principles, clarified how we understand the classical theory a little bit more. So, I'd like to say something about that.
Well, I would say the two most simplest and obvious things to say about both those topics. First of all, as far as the difference between relativity, general relativity and earlier theories, certainly that was something that people pointed out. That somehow or other the intuition that physicists had is that accelerating charges generate electromagnetic waves, so then surely accelerating masses emit gravitational waves. But since the whole point of general relativity is to relativize acceleration, that begs the question, what is an accelerating charge? It goes back to that whole question of if I drop one mass and hold another, which is the one that I'm accelerating? And certainly, I didn't mention it at all, but a big reason for interest in gravitational waves in the post-war period was just the question of, can we quantize the gravitational field? And we know that in the electromagnetic case, the study of the wave aspect of the field was played a considerable role in the quantization of the field. So there was some expectation that the study of gravitational waves would give some clues as to how to quantize the gravitational field as well. And I think that was one of the major motivations of the gravitation. There were others.
Concerning your second point, yes. At the beginning, when Alessandro and I were thinking about, we have a two-body problem, so you have two bodies. And if you start saying this should be in correspondence, in some sense, or equivalent to one body in a metric to be found, when you say that, this is up in the air, okay? But you need a dictionary, okay? And this is where the quantum way of thinking is useful, because in this dictionary there is something very clear, that you have quantum integer numbers on both sides, and then immediately you say, then I know the dictionary to identify these integer numbers, and you just have the freedom of the energy transformation. So it helps conceptually in posing the problem. A posteriori, you can just say the low and things like that, but it really helps conceptually. And Mr. Wheeler writes about, for instance, it's Hamilton-Jacobi. It's clearer, the result of the Jacobi thing is clearer if you think quantum mechanically. Why the Hamilton-Jacobi thing?
There's microphones back. Oh, it's over there.
Okay. I'd like to draw attention to the fact that the very first idea of Einstein when dealing with general relativity, his very first idea to explain light deflection was considering a variable speed of light. And this was outlined in a paper in 1907, another paper in 1911, 1912. And these papers remain largely unknown because Einstein again did an error. Did not consider variable length scales, just variable time scales. And it took almost 50 years until this error was corrected by Robert Dickey in a 1957 paper that was actually a precursor of the rather well-known Brown-Sticky theory, but it's rather unknown also this paper by Robert Dickey. And with regards to gravitational waves, Robert Dickey obtains all the classical tests of the results, but there is no necessity for gravitational waves in this form of the theory.
The next question here, do either of you want to make a comment in response to that?
Well, I was going to take the opportunity to mention Ted was saying, that many of these errors that I alluded to turn out to be slips on closer examination. And I think that's true. Working on the Einstein Papers project, one does, after a while, feel bad because it's somehow one's job to find every lousy little slip of the pen that poor Einstein ever made and draw the reader's attention to it. But of course, there are slips and there are slips. So I think with regard to the slip in the factor 2 of the quadruple formula, we still usually say Einstein produced the quadruple formula in 1918, so somehow we say, well, it's not that important, that slip. Whereas the slip from the 1916 paper leads to much more serious consequences, which came from the quadruple.
Just a short remark, historical remark on the direct and indirect evidence for gravitational wave detection. I remember at the conference when it was first announced that the slowdown of the Taylor price, this was taken as an evidence for gravitational radiation. Virginia Trimble stood up, the wife of Joe Weber, and opposed this interpretation by saying it is not clear that the system is clean. And I think what she meant is that there could be matter from one companion to the other, so there could be other means by which maybe the slowdown is caused. I think now we know better, but at those days it was critically.
Josh.
I want to go back to the Einstein-Rosen paper, because you made an offhand remark there about Bondi, Pirani, and Robinson clearing that up. But you never said why or how they cleared it up. The issue there was that up to that time after the World War, the Schnerowitz group was very active and taught us that boundary conditions are very important, and jump conditions across boundaries are very important. And then Papapetro showed what the boundary conditions, what jump conditions you had to have across null surfaces. And so that Bondi, Pirani, and Robinson were then able to look at the Einstein-Rosen work and place a plane wave between two null surfaces, so that everything was nice and finite and everything was non-singular.
Thank you. Should be bringing this to a close. Are there any more questions? One more? Oh, so
it's not last questions.
I think Madame Jacques asked this question and she's still not happy with the answer or lack of answers. So I do think it is certainly true that we do not have a local notion of energy or stress-free tensor, which is gated value. But the statement is, in fact, and this is where to talk about in a precise manner about the energy carried by waves, even in Maxwell theory, even in Minkowski space-time, it is incorrect to just use the Poynting flux, because even a charge which is sitting, just sitting and doing nothing in Minkowski space, which is going to field, if you looked at an appropriately boosted frame, a long cylinder, you'll find that there is actually a Poynting flux, but of course it falls like 1 upon r to the 4th, and therefore the total energy that is radiated falls like 1 upon r squared. So in the limit, however, that goes to 0. But at a finite distance, it does not go to 0. And that is where going to infinity is important. And now coming back to the question, the statement for general relativity is that if you, say, with a 0 cosmological constant, that if you go out to infinity, to scry, then in fact, there is a precisely defined connection on scry, and the curvature of this connection has an invariant piece. The curvature of this connection is a 3D manifold, it's degenerate metric, so you have to be a bit careful, but it's well defined. So there's a curvature of this connection, that is a bond-induced tensor. So we say that there is gravitational waves if in fact the bond-induced tensor is non-zero, and it's curvature, so it's not coordinate dependent. And we say it's not that if there is a, and the energy that is carried by these gravitational waves using Hamiltonian methods can be written explicitly as in terms of the square of this bond-induced tensor. And therefore, we have a formula, not at a finite distance, but we do have a idealized formula in the limit that goes to infinity. And I think it's completely unambiguous. I mean, this is the point that I want to make.
I do agree that Schopenhauer has put her finger on two very key points, which played a major role in the actual history. Certainly, people recognized that for historical reasons, there was a natural tendency to focus on this question of do the waves carry energy, and it was pointed out time again that it wasn't entirely clear that this was a good quantity to examine within the context of general relativity. And that is something that I guess I will advertise at this point my book on the subject, which does at least go into a little more detail on just that topic.
Okay, well, I think we need to bring it to a close. We have a coffee break, but thank you both for